B calculus, we are going to start 7.4 and do 3 pages here on exponential growth and decay. All right, so here's our notes. Let me tune in here and let's get started. Growth and decay. Okay, so we're going to use exponential functions to model growth and decay in applied problems. Okay, so just a little warm up here. True or false? And illustrate the concepts gradually. In linear growth, the rate of growth is constant. Okay, well, linear, there's a keyword there, rate of growth is constant. That would be true. You get, m, you get your dy dx, which is your slope, and certainly here, the dy dx is constant. All right, but in exponential growth, there's just parent function there. You can see that dy dx, which is m, changes. All right, so this is false. And this is true. Pretty basic. All right, let me get my glasses on. Write and solve the differential equation that models this verbal statement. Then evaluate the solution at the specific value, the specified value of the independent variable. All right, so we're just going to read. A keyword here is going to be when you read proportional. All right, proportional is going to bring in that back from algebra, that y equals kx concept. All right, but it's not a linear because this says rate of change. But the thought process is the same. When you read that proportional, really what you're thinking is that this constant comes in, this constant of variation. Okay, so the rate of change of y, so that would be dy dx, is proportional, okay, rate of change of y with respect to x, so that gives me that dy dx. So, read, of course, here and here to get your variables in there. Is proportional, so then bring in the k to y. All right, so 2 pieces of information here. We've got 0, 4, if y is 4 when x is 0, and when y is 10 when x is 3, there's another piece of information. What is the value of y when x is 6? Okay, so we are going to use the 2 givens to write a formula, an equation, so that we can solve for when x is 6. But first we have to get it into a spot where we have an equation to work with, and that is going to require some integration. All right, so we're going to integrate, or we're going to separate the variables first before we integrate. So 1 over y dy, and it's just a constant dx. We'll keep that over there with x, because our ultimate goal is to get y equals. So as simple as we can on the left with our y stuff. All right, so let's integrate that. Okay, so this is going to be the ln of absolute value of y equals kx plus c. Okay? So we've gone through the motions here. We're going to exponentiate both sides. So we're going to get the absolute value of y equals here e to the kx times e to the c. All right, and so then deal with the absolute value. It's going to be plus or minus e to the c, e to the kx. We're going to let big capital C equal this plus or minus e to the c, and now we have our formula. Okay, so we can work with these 2 given points to answer the question. So the first one I want to work with is this one with the 0. It's going to be really nice to get a 0 up here. This would be your initial value, right? When x, which will turn into time, is 0. We have a y value of 4. So that is going to be a good thing to start with. And so 4 equals c e to the k times 0. Anything to the 0 power is 1. So we get that our c value, that is just 1. that our C value is 4. All right, so our equation is progressing nicely. Okay, so now we've got to find this K value, and so we'll use our other data point to do that. So here's where I used 0, 4. All right, and so now I'm going to take this and use 310. Okay, so 10 equals 4e to the k times 3. Okay, so isolate 10 over 4 equals e to the 3k. ln, and let's just do 5 over 2, equals ln of 3k, e to the 3k. All right, and so that's going to pull the 3k down. And that's just going to be gone. So k is going to be equal to the ln of 5 over 2 over 3. Okay, the ln of 5 over 2 over 3. All right, so let's grab a calculator and just see what that's equal to. You see that okay? The other calculator doesn't have that dot, but that's all right. All right, ln, I'm just going to put in 2.5 in the parentheses and divide it by 3. Okay, so k is going to be equal to 0.305430244. And maybe I'll just even store that. So store, and we'll just call it alpha A, enter, and we're stored. So now let's do the rest of this. I should have started a little more to the left, but I'll just write small over here. So let's solve the question at hand. Our formula then is y equals 4e, alpha A here, okay? And you could even keep this just intact and write that up there, however you want to do that. But where am I? So I'm just going to write alpha A here, making note that this is right here. And we're plugging in 6. All right. So to answer the final question here, we'll just go 4e to the 6 alpha A, enter. Okay, and it comes out to 25. All right, so there's a progression there of just kind of an exponential growth and decay problem. Okay, so this theorem is the exponential growth and decay model. All right, suppose y changes at a rate proportional to the amount present. Okay, so we're just not doing numbers in general. We're actually doing growth and decay of the amount present. And y sub 0 is the value of y when t is 0. So initial, right, the initial value. All right, then the solution to the initial value problem. All right, and so suppose y changes at a rate proportional to the amount present and y sub 0 is the value of y when t equals 0, then the solution to the initial value problem, ky, all right, where y sub 0 is equal to that plug-in of 0, and this is going to be the initial amount e to the kt, an exponential function. So if k is greater than 0, this is going to be growth. And if it's less than 0, it's going to be decay. So be able to derive this formula, or on the AP exam, if you use it, be able to call this the law of exponential change. So it all depends on when you're given a rate, and this world proportional, and the amount present, which means not the time, right? The time would be the x value, but the amount present, which is this y, which is why it's written right here. Okay, next page here. Do 3 pages here. This is our second one. Okay, so we're going to see where the formula came from, which is really quite cool. So review, compound interest. We use the formula A equals P 1 plus R over N to the NT when we compounded at intervals, so like monthly, daily, hourly, all right, at these intervals. However, if it's continuously, that's an exponential situation, and we have this PERT formula. And doesn't that look very similar to what we just did, the A sub 0 or the Y sub 0 if this were Y, and then KT. So we're going to go through and actually do that here in the notes so you can see where PERT came from. Okay, so we can model this growth by the amount of money added continuous at a rate proportional. So we bring in that K, and the K here is going to be in PERT a rate. So K is the rate in the formula, which makes sense. And then it's proportional to the amount present, which is our Y, but in this particular situation, it's the A here. Okay, this is going to look incredibly similar to what we just did. So we're going to separate the variables. Okay, so we'll divide out the A, and we're going to get this R dt. Okay, so R is, these aren't compatible, but remember R is just a constant. Okay, so I've got to watch my time here. Okay, so this is ln of absolute value, or we got to integrate it, so I'll do my symbol here. Ln of A is going to be equal to RT. Okay, we're bringing in the T plus C. All right, exponentiate both sides. So absolute value of A is equal to e to the RT times e to the C. Deal with absolute values, plus or minus e to the C, ERT, and let's let, you could let P or A sub 0, right, but we're going to, since it's PERT, we're going to let P equal plus or minus e to the C, and we have, right here, we have amount equals, doesn't matter what we call the constant, so for PERT we call it P for principal, which is an initial amount, ERT. So there you go. There's PERT. Okay, and this came from the, this, and I really, right here, this R, and then this amount present in general. All right, and then we've got this clarification here. Which makes sense. You're starting to grow your money. We're at time 0. You've got your initial amount. At time 0, you have your initial amount. Okay, let's do another one. All right, so this one reads, the saving accounts earning compound interest, triples in value over 12 years. How long will it take the original investment to quadruple? Identify the given information in order pairs. So at time 0, we have an initial amount. Okay, and at time 12, we have a tripling. So how long will it take it to quadruple? So we're looking at some time to do 4 times as much. Okay? All right. And so it says to derive the formula here, but we just did that. And so for the sake of time, I'm just going to say see above. Right? But do get used to kind of that flow of how it moves from the words in the prompt to the formula. Okay, so we're dealing with A equals P e to the RT. All right, so at time 0, we have got a 0, all right? And then here we have, at 12 years, we have 3, the initial amount. So since we've already got the formula, we're just going to go right here and just say, well, we've got 12. We've got 12 as our time, and we've got 3 times the initial amount at our end. So I don't know my initial amount, so I could do this, and you could easily just put, I'm going to put that there, but with these, times 12 here, I mean, with these, whatever the situation, if it's compounding in intervals or compounding continuously, if you're tripling, you can use $1. So you could just put, nothing here, meaning 1, and you could just put 3 here. But I'm just going to keep the a to the 0 here. So this is the second data point. Okay, this one doesn't really come into play because we already have our solution, we already know perp. And so this is just going to go 3 and here. So these would cancel, and so there you go. This is like just using a hypothetical dollar. All right, so we're going to ln 3, and we're going to ln e to the 12r. Okay, so we're going to get ln of 12, ln of 3 over 12 is our r. ln of 3 over 12. Okay, so let's see about this quadrupling. All right, I want to do a little thing here. So we're looking for 4. Okay, e to the r, which we know now is ln of 3 over 12 times r. Okay, so, these could, I'm going to show this 2 different ways. So these could go, and this would be 4 equals e to the ln of 3. And what's kind of a nice thing to do here is to think of this as ln of 3 times r over 12. Okay, so all I did is kind of slide that 12 over. And when do we multiply our exponents? Well, power to power. Okay, so what happens here then is those are inverses, and so you get 4 is equal to 3 to the r over 12. All right, don't worry, I'm going to go through this another way too so you can see your options. Okay, so at ln this side, okay, ln this side, so I'm going to go ahead for time and pull this down in front, ln of 3. Okay, and so we're going to see that the r is equal to ln of 4 divided by ln of 3 over 12. Okay, so that is going to be ln of 4 divided by ln of 3. Let's put that in parentheses. Divided by 12. All right, and so this is going to be this 15. Oh, sorry, and this is t. My bad. You guys are probably cursing at the, well, you don't curse, right? You're probably waiting for me to catch that, right? All right, this is t. R was this. This is t. So t. All right. So t is equal to, what did I say? 15.142 years. All right. So, if you don't like that little maneuver, that's fine. It will all work itself out. So let's see. What if we just picked up here and did not do that? What if you said, okay, I don't like that, and just did ln of 4 here, and then ln of e. So this is a little messy for me, but it still works. So you'd still be at ln of 3 over 12, which is your r, times t. There, got the t right. Okay, so what would this do for us? That would be gone, all right? And you'd get ln of 4 equals ln of 3 over 12t, and voila, same result. Which of course is the same thing here, so t is 15.142 years. So same thing. So you don't have to do this little maneuver, but this is kind of cool when you kind of see where some other formulas you've seen before. like the half-life formula, you can see why you divide by that 12 there. That kind of shows you how that came to be. Okay, so we're going to do one more here. But I'm going to pause because my kids are texting me on my phone. So hold please. Okay, so number of bacteria in a culture increases from 600 to 800 in 2 hours, assuming that the rate of increase is directly proportional to the number of bacteria present. Find. Okay, so this is the law of exponential change. So you can go through and do dy dt equals ky and do a quick derivation here. So 1 over y dy equals k dt. Integrate, ln y equals kt plus c. Exponentiate. Absolute value of y equals e to the kt times e to the c. Y equals plus or minus e to the c, e to the kt, and let plus or minus e to the c equals, say, whatever, you can use c, doesn't matter. All right, so we have our formula, which is y equals c e to the kt. Or you can start here and say, by the law of exponential change. Okay, by the law of exponential change. Okay, and so, this point here is 0, 600. All right, and I think on the test we say to derive it, so don't depend on this, be able to maneuver here. So 0, 600, 0 is going to go in here, that's going to zero out. C is going to equal 600. So we'll just show that from that data point. So 600 is C. So my formula is y equals 600 e to the kt. Okay, we're going to use our next data point that in 2 hours we're at 1800. Okay, there's my official kind of, well, not yet, it's not official till we get k. This is 1800 equals 600 e to the k times 2. Right, so 3 equals e to the 2k. All right, so ln of 3 is equal to 2k ln of e. So just, did an ln of both sides, the 2k came in front. So k is equal to the ln of 3 over 2. Okay, so now the official formula is y equals 600 e to the ln of 3 over 2 times time, okay, or y equals 600 3 to the t over 2 by how I showed you above. Either one is fine, and we'll get you full credit on either exam. I just like this one better. I don't know, that's all just kind of messy to me. All right, so find the number of bacteria present at 4 hours. Okay, and so that's just 4 over 2, which is 2, which is 9, 5,400 bacteria. Okay. All right. Next one. All right, sketch a solution of all of the differential equations on the slope field through 0, 6. That's right. Sketch a solution of the differential equation. I was about to say all the different. Okay. Sketch a solution of the differential equation on the slope field through 0, 6. Solve the differential equation for the particular solution. Show all steps. All right, so 0, 6. Okay, so we've got this here. Okay, at y equal to 4. So you can see that you've got all of these decreasing slopes here, all of these increasing, so we can, see that this is going to be exponential. And so yeah, it's going to look, something like this, right? But let's just show it out and get some confirmation on this. So we're going to be looking at some exponential decay, and we're going to be looking at some sort of shift here of the horizontal asymptote. All right, so when does dy dx equal to 0? Well, that's at y equal to 4, and there are increasing slopes when y is less than 4 below it, and decreasing slopes above it. So we already just spoke to that. These slopes are positive here, okay, and these slopes are negative up here. Okay, that's pretty easy. All right, so here we go. Separate the variables. So I'm just coming from here, you guys. dy 1 over 4 minus y equals just r dx. Okay, so this isn't the exponential law of change here. This is just some random formula. So if it's not something that you have to write by the exponential law of change, they'll give you a formula. All right, so integrate. Okay. So, this is you're going to have to use ln here, but think about some u sub. So with u sub here, again, we would need a u sub here because if you were to differentiate this, it would have a chain, right? And that chain is -1. Well, with u sub, that's just going to bring that -1 out front, so that's pretty easy. All right, so this is going to be negative ln 4 minus y here, and this is just going to be x. So you just use the variable that, this is, what's back here, plus c. All right? Okay, so I like to isolate the ln, so I'm going to send the negative over, okay? And so as we talked about in class before, the c does not receive arithmetic. So the c doesn't receive adding anything to it or multiplying anything. So I don't need to make that a negative c. It doesn't matter. It's just a constant. It will receive function actions, though. So if you have to square root both sides, it'll receive that. If you exponentiate both sides, it receives that. But it does not receive arithmetic. So we just apply the negative to the x. Exponentiate. All right, so here we go. Problems flow very similarly. Okay, so let's let c equal plus or minus e to the c. So 4 minus y equals c e to the x, negative x, sorry. Okay, which makes sense that we have this decay. We've got this negative value right here. All right, and then so this is going to be minus y equals, so right here is where I would, right away, this is where I would, stop once we get the big C in here, not this C, but the big C in here. This is where I would put in the 0, 6. I think that is the best place to put it in right here. So this is 4 minus 6 equals C. Just as soon as you can get that initial in, I would. You can put it in anywhere you go, but my recommendation is right away with the exponentials. As soon as this is, cleaned out, put that in there. All right, so anyway, so e to the, negative 0, it's just going to be 1. So C here is negative 2, okay? All right, so where am I? So 4, and then you go right back to where you plugged in. So right back here, once you get here, go right back. 4 minus y is equal to negative 2e to the negative x. Okay, negative y is equal to negative 2e to the negative x minus 4. And last but not least here, I've got y equaling, so this is going to negate 2e to the negative x plus 4. Okay, so that is the equation for this slope field, and you can see the consistency here with this vertical shift of plus 4 and that horizontal asymptote going up 4, and the direction of the curve, and everything should just make sense in terms of Algebra 2 to calculus. Okay, I'm going to pause the video for just a second. I'll be right back. Okay, last problem. So far, all of the examples have given the initial value. What if you're not given the initial value? Okay, so here we're just giving 2 data points, 2 points to work with. So we are going to use a system. Okay, we can't get that initial and then use the initial to get the k. So no x sub 0 here, so we have to use a system. All right, so one system will be 1 equals a e to the kt, and the other will be 5 equals a e to the k5. All right, so we want to solve for one of the variables, right, and then plug one equation into the other. I'm going to use a substitution here. So obviously a is going to be the one we want to solve for. So 1 over e to the k is equal to a. All right. And so, remember this is that initial amount, so it's the same a. And so this one, 5 over e to the 5k equals a. All right. So if a equals this and a equals this, then I can set these equal to one another. Okay, so e to the 5k here equals 5e to the k. All right, and I'm going to divide out the ek here. And then I'm going to subtract. So e to the 4k equals 5. All right, so let's ln e to the 4k, ln of 5. So 4k equals ln of 5. K then is ln of 5 over 4. Okay, so what do? When you solve a system, you plug back into one of the originals. One or both. Maybe both to check, but I'm just going to pick the easiest one. So I'm going to resub back into one of my 2 originals. Okay, so this is a 1 over e to the ln of 5 over 4. All right, and let's just say we don't have a calculator. We can use our little trick here to e to the ln of 5 times 1/4, which is e to the ln of 5 to the 1/4. So that cancels, 5 drops to the 1/4. So a to the 0 is the 4th root of 5 here. 1 over. All right, so our formula then is going to be y equals 1 over 4th root of 5 is our initial, e to the kt. So e to the k, 4, y equals 1 over 4th root of 5, 5, right? So that's canceling, that's dropping, that's been pushed over to the t over 4. All right, so let's check that out on the TI, see what it looks like. All right, so 1 divided by 5 to the, I'm going to do 1/4. I guess I need, I wonder if that'll be okay. Well, I guess I'll read that as the whole denominator. All right, times 5 is kind of risky. It makes me a little bit nervous. We'll see what happens. Times up to the t over 4. Zoom 6. And there we go. All right? So just like that. And let's just look at, here, this is this graph. Let's just go ahead and look at what this is equal to. So about 0.66 here. So that's a little low there. So we'll go a little higher, about right here. That initial amount. Okay, and that's 0, 1 over root 4. All right, so there you go. Good luck, and we'll see you guys when I get back. All right, take care.